Okay. Before going on with the discussion, I'm sorry, I just remembered that now. But during the lesson, the last lesson, while I was discussing the um, electronic levels that appear in the system due to the application of a magnetic field, and using in particular the fact that the levels can be grouped into cylinders. Just by looking at the registration of that lesson, I noticed that I was talking as if the Hamiltonian was the Hamiltonian of the quantum mechanical oscillator, but I forgot to add the power of 2 in the, let's say, potential contribution of the Hamiltonian. So I'm not able to correct that on the registration, but please just remind the fact that the actual Hamiltonian was quadratic in the kinetic term and also quadratic in the potential term, as I wrote in the in the potential term, I just wrote 1 y minus y0. I forgot to include the power of 2. So please include the power of 2 in that Hamiltonian, as that is the correct expression and is in agreement with the procedure. I just forgot to write that while writing the equation here on the blackboard. Okay, so sorry for this short comment, but I just remembered that I made that mistake during that lesson. So what we have just seen is that in discussing what happens when we consider the electron interaction using the Hartree approach, is it possible to write the full Hamiltonian as a sum over one-body Hamiltonians. Now, what happens when we apply this new structure to the n-electron wave function? Just to rewrite that, in principle, the n-electron wave function should include both the coordinate and the spin state. From now from now on, just to simplify the notation, I will just write down the position coordinate. But please remember that in principle, we should also recall the fact that each electron has a specific spin state. So for the moment, I will just write this as a function of the coordinates. So I'm not removing the spin, I'm just avoiding to include here the spin state of the electron. So what happens when we apply this Hamiltonian to the wave function? So now in principle this is now the new problem. So we should write here this as a and this should be equal to the total energy of the system times the electronic wave function. The fact that here you have only a specific index, so this Hamiltonian is an operator that from all the possible coordinates within this wave function acts only on the coordinate of electron I. So all the other coordinates here, if we fix the value of I, all the other coordinates do not contribute to the calculation, just the I coordinate contributes. Due to this fact, so when we apply HI to this structure, this means that only the coordinate of that electron is affected by the action of this operator. All the other coordinates are just coefficients. So due to this fact, what one tries to do is to rewrite the full n electron wave function into the combination, sorry, as a product sorry, I used the index I twice. So in this case, what one tries to do is to rewrite the full n electron wave function as a product of single electron wave functions. So this is just the product of all the possible wave functions that you may have in the system, considering the total number of electrons that you have at disposal, and then you make just the product of those. So in this way, when you apply this Hamiltonian, when you apply this Hamiltonian to this product, the result is that you have just the product from J that goes from 1 to N with J different from I, from I of times the application times the contribution of the application of the Hamiltonian to just one wave function. So due to that, what is the result of that? That using this kind of structure for the n electron wave function, at the end, what you need to solve is just the Hamiltonian concern regarding just one electron, because at the end, if you fix, let's say, the Hamiltonian, the single so each Hamiltonian is depending on the index, and the index refers to one specific electron. But as the index here is arbitrary, we may just rewrite that as so. At this point, since all those Hamiltonians are equivalent with each other because they have all the same structure, what changes is that it's just the index of the coordinate, but then the Hamiltonian is the same for all the electrons. So due to the fact that all the those Hamiltonians here are equivalent with each other and just the index changes, then we may reduce the problem to the solution of just one of those. So at this point, we have again a one electron problem that somehow masks an n electron problem. So we switch from an n electron problem to a one electron problem. What is the residual difficulty that we have in this approach? The residual difficulty is due to the evaluation of U of L, because U of L of R is equal to minus C, the integral of the total charge density in position R prime divided by R minus R prime. And for the evaluation of the total charge density, we have the summation over I of minus C and then we have the square modulus of all the possible wave functions. So the actual problem now is that to evaluate the solution, sorry, I forgot to include here the wave function of the electron. So to solve the problem, we need to know the solution, because the solution has to be included in this charge density. So to find the actual solution, due to the fact that the capability to obtain a solution actually depends on the fact that you should know what is the solution, the problem is solved by performing iterations. So you start with the initial choice of the wave functions. For instance, you may use block electron wave functions. Then you use those wave functions to evaluate the electron-electron interaction potential. You introduce that into the Hamiltonian, you solve the problem, you find a new solution, then you use that solution to estimate the electron-electron interaction potential, and then you solve the problem again. When the solution at a given step is very close to the solution that you obtain at the following step, then you consider that this iteration may have come to an end, so you have the actual solution of the problem. So the fact that we now have removed the complexity that was due to the use of an electron wave function, and that complexity was reduced down to the use of just a one electron wave function, let's say we have to pay for this reduction, and we have to pay in the sense that we have to use this iterative approach, so to find the actual value of, so to find the actual set of one electron wave functions that solve the problem. And if compared to the, let's say, value of the energy that we had in the independent electron approximation, we will have a new value for the energy corresponding to a one electron level. So please note that in this case, the let's say, instead of discussing of energy of the n electron system, we discuss of energy of one level. And what we expect is that the energy of one level in this new configuration will be different from the same energy of that level in the independent electron, using the independent electron approximation. So a side effect is that we go on considering the system to be a system where we have single electron levels, even if we consider the fact that the electrons are actually interacting with each other, and the effect of that interaction is a modification on the energy. So you somehow include the effect of the electron-electron interaction not on the structure of the levels, because you have always single electron levels, but on the value of the energy. So in this case, the modification is on E. So E will be modified with respect to the single electron case, and this modification will be an effect of the interaction. So if we now, let's say, want to just make a short summary of this kind of approach, the approach is to use the total electron density to rewrite the Hamiltonian as a sum of one electron Hamiltonians. Thanks to this configuration, we may write down the n electron wave function as a product of single electron wave function, so single level. We consider here this as a product of single level wave functions. So this is a dramatic reduction of the mathematical complexity, since we have a one-body problem here, and also at the end a one-body wave function here. So we are switched down to the, we are again the one-body problem approximation. So the interaction that in principle means strong interference between the levels. So in principle, it should not be possible to consider single electronic levels. But in this approximation, we again refer to single electron levels. So the structure of the problem is exactly the same structure that we had for block electrons, so single electron levels, and the effect of the interaction is just included in the energy. So again, single electron levels that will be different from the single electron levels that we had without the electron-electron interaction, because now we have a new potential term here. But the effect of that is not on the structure of the problem, but just on the energy. So the energy can be considered as a sort of effect, a sort of modification, so includes the modification induced by the fact that we have switched on the electron-electron interaction. This approach was presented at the end of the 20s in the previous century, when the properties of the fermions were known. So they knew that the fermions had to follow the Pauli exclusion principle, and in particular, they also knew that if we consider an n-electron system, if you exchange two electrons with each other, then you should observe a change in sign of the electronic wave function. But if we consider the if we consider this so if we consider that the n-electron wave function is just the product of single electron wave functions, if you exchange any two electrons, you will never observe a change of sign in this electronic wave function. So one comment is that this structure for the wave function is fine for what concerns the reduction of the mathematical complexity, but is not fine from the point of view that this wave function here has not the right symmetry that we expect to have for a fermionic wave function. So here, this proposal for what concerns the n-electron wave function is not in agreement with the behavior that we expect for electrons. So due to this feature, a new approach was developed to try to, let's say, combine this approach. So the fact that the actual electronic wave function, n-electron wave function, could be written down as a multiplication of single electron levels, but to that we have to sum the fact that if we exchange two electrons, then we have we expect a change of sign in the electronic wave function. So what they try to do was to combine this peculiar property with the fact that the actual electronic wave function needs to be antisymmetric with respect to the exchange of two particles. And this combination, so this combined approach, is what is called the Hartree Fock approach. And let's say this approach is based on the use of the so-called Slater determinant. And what is the aim of that? If we consider, just to make an example, if we consider just two electrons, then if we want to build up a wave function for those two electrons that is written as a product of single electron wave functions, up to now we have done something like this: electron 1, level 1, electron 2, level 2, just multiply those two values and we have the wave function. But this is not antisymmetric. So a right solution for what concerns the antisymmetry of the wave function should be to include another term here, that is this one. So in this way, if you use this this term here, what you have is that the if you exchange electron 1 and electron 2, then you have that actually you have the appearance of a minus sign in front of the wave function. Here we also need the denormalization factor. So in this case, again, if you use this structure, you may actually have antisymmetry. This structure can be written in a more compact way. So if you consider this matrix, a matrix where you have in the rows, you fix the level and you change the coordinate. And in the columns, you fix the coordinate and you change the level. If you make the determinant of this matrix, then the determinant is exactly this term here. So the idea was to write the wave function to use for the in this two electron approximation. So if we suppose just to have two electrons in the system, then a possible good choice for what concerns the electronic wave function that describes those two electrons and also include the antisymmetry that we expect that the two electron wave function should have, is to refer to this determinant. And this determinant is called Slater determinant. The Slater determinant was proposed as a starting point for this calculation at the beginning of the 30s in the previous century. So just a few years after the Hartree approach was presented. So in this, let's say, two electron system, this kind of determinant could be a fine wave function that combines the product that we have here and here. So it's easier to handle, let's say, it's easier to handle this product rather than a single wave function where the coordinate of electron 1 and coordinate of electron 2 are intermixed with each other in a complicated way, with the fact that we also need the antisymmetry to have a proper, in this case, two electron wave function. So the idea is to, let's say, following this example, to export the same mechanism in the case that when we have n electrons. So the idea, the proposal was to use this later determinant also in the n-electron case. When we switch to the n-electron case, the complexity of the evaluation of this determinant is huge because we have a matrix that is n per n, when n is of the order of 10 to the 28. So we have a huge matrix. And let's say in this case, in a 2 per 2 matrix or 3 per 3, the determinant can be evaluated quite simply. So the problem is how to export this solution to the n-electron problem by writing that down in a way that can be also used to handle a calculation. Because if we just write that down as a matrix, then it's quite difficult to use the matrix within the Schrödinger equation. So how may we rewrite this determinant in the n-electron approximation? The solution is the following. If you notice here, please just refer to the structure of this two-electron wave function. Please note that here you have, if you fix, just look at the coordinate 1. In this case, coordinate 1 is associated to level 1. In this case, coordinate 1 is associated to level 2. So starting from level 1 and level 2, in one case, we associate 1 to 1. In the second case, we associate 1 to level 2. This can be written as, so we are making a sort of permutation. So in one case, we associate 1 to 1, in the other case, 1 to 2. So the possible index corresponding to the level that we associate to a fixed value of the electronic coordinate, so that we associate to a specific electron, can be considered to be a permutation over the possible electronic indexes. So this structure here can be written as wave function of electron 1, P1, wave function of electron 2, P2, and in this case, P is identity. So 1 corresponds to 1, 2 corresponds to 2. So P1 is equal to 1, P2 is equal to 2. And then we have minus phi of R2, phi of R1. And in this case, we have a new permutation of 1, a new permutation of 2. And in this case, to 1, we make correspond 2 to 1, and we make 1 correspond to 2. Because in this case, the permutation of 1, please, I just cancel. I have to maintain the same order of the indexes within the wave function and just let the permutation switch the indexes here. So if you notice here, coordinate 1 corresponds to 2, so 1 to 2. Coordinate 2 corresponds to 1, so 2 to 1. So in this case, we have that using permutations, we may rewrite the wave function. And what about the minus sign here? The first permutation, 1 to 1, 2 to 2, is an even permutation. So we may associate the sign, a sign to that permutation that is positive. Differently, this permutation is uneven, So we may associate to that permutation a minus sign. So the minus sign here can be associated to the sign of the permutation. So in a compact way, this can be written as a sum over all possible permutations of where here, in this case, I have just two permutations. One is identity and the other is the switch, because I have just two particles. So P will be identity or switch. So just two terms in this summation. This minus with the index P just mean sign of that permutation. So when we consider the permutation to be identity, the sign of identity is +1, is positive. So we have a positive sign here. When we consider the switch 1 to 2, 2 to 1, then the sign of that permutation is negative. So we have the minus here in front of the combination. So in this way, it's possible to write down this later determinant in a compact way. So the solution, in case we consider the n electron problem, is the following. For the n electron problem, the wave function is equal to the sum over all possible permutations. And here we have okay, so this is the structure of the Slater determinant. What we need to evaluate now is the normalization coefficient that we may assign to this Slater determinant. So we may just check whether this wave function is normalized to 1 or not. So the idea is to evaluate the square modulus of the Slater determinant. The only thing we assume here before evaluating this square modulus is that the single electron level are orthogonal with each other. So we assume that if we make the this scalar product is equal to 0 unless the index of the levels are the same. So just this is the only requirement that we make considering the single electron wave functions. So at this point, to write down this square modulus, we may use one set of permutations for this side of the scalar product and another set of permutations for the other side of the scalar product. So what we may write down is this. So we have a summation over P, that is the first set of permutations, and the summation over Q, that is the second set of permutations. And then we have first then we need to include the sign of a specific of each permutation of the P group and the sign of each permutation of the Q group. In this situation, due to the fact that let's just consider coordinate 1, just to make an example. If you consider coordinate 1 here, this is found for level Q of 1. So the index of the level depends on the specific permutation you are using here. But on the other side of this cross product, you have the same coordinate that is in level P1. If Q1 is different from P1, then the scalar product is 0, due to the fact that we assume that the single electron wave functions are orthogonal with each other. So the only possibility to have that this is different from 0 is to require that P1 is equal to Q1. But the same, let's say, the same thing may be applied to, let's say, Q2, Q3, Q4, and so on up to Qn. So the requirement to have that this result is not 0 is, so this is different from 0 if P is each P is exactly equal to Q. So only in that case you have that, you may have non-zero terms coming out of this scalar product. So at the end of the story, you have that that this is equal to a summation over P. I just choose P as to just say a set of permutations. So here you have so the only solution is to have the same permutation on both sides of this product. Now the sign of the permutation disappears because whatever the sign of one permutation, the sign of the other permutation will be exactly the same because we have the same permutation. So here you have just one, so a positive sign for in all the cases. In this situation, we have a sum over permutations. Each term here gives us a value equal to 1, because if we fix the value of P, then we have scalar products that, and each of those gives 1 as a result. So each scalar product here gives us a 1 value. And we have a 1 value for each of the possible permutations that we may consider in this element, in this set. P is a permutation belonging to the possible permutations of n elements. So the total number of permutations is factorial n. So due to the fact that this scalar product gives you 1 for each of the permutations, and the number of permutations is factorial n, then this scalar product is equal to factorial n. So the normalization coefficient that we have to apply to the Slater determinant is 1 divided by the square root of factorial n. So here we may include 1 divided by the square root of factorial n due to this term. So now the final expression that we may use for the Slater determinant is 1 divided by the square root of factorial n times the sum over all possible permutations of this product here times the sign of each specific permutation. I make you just one question. From now on, I will present you some calculations involving the Slater determinant. And to understand those calculations, let's say the fact that why I suppressed here one permutation, so why I switch from this expression here down to this expression here will be recalled during all the calculations. So do you have some comments or questions concerning this point? Because if you understand that I think you will understand everything else in the following. But if you have some doubts here, please let me know so we may discuss about those now.
It is okay.
Okay. So if it is fine, what I would like to do now is to evaluate the expectation value of this the Slater determinant of the of one electron and two electron operators. And why should I do that? Because the idea is the following. I just changed the page. Yeah, we saw that the Hamiltonian of the system is equal to a summation So here we have the kinetic term and the potential term, the potential due to the interaction with the ions, are operators that depend just on the coordinate of one electron. So we may consider this to be a one-body operator, and this is again a one-body operator, where one body means the action of the operator is refers just to the coordinate of one electron. If we consider the electron-electron interaction, this is a two-body operator because this involves the coordinates of two electrons. When we will apply the Hamiltonian or to this Slater determinant, or when we want to obtain the expectation value of the Hamiltonian over one of those operators, for instance, to evaluate the energy or some other parameters, so we may say that we have to handle two different situations. One situation is the operator is a one-body one. The other situation is the operator is a two-body one. So that's why I would like just to make a general calculation now, so to do not make it that for each of those operators. And the general calculation is what happens if I want to evaluate the expectation value of a one-body operator over this Slater determinant. Second step, what happens if I want to evaluate the expectation value of a two-body operator over this Slater determinant? So I start with this one here. So what I would like to do now is to evaluate something like this using this Slater determinant. I call the operator A. So A has no meaning, it's just a letter to identify this one-body operator. One-body operator that acts on the coordinate of electron I. So that operator acts just on the coordinate of one specific electron. And then we have again the one-body operator. So we know that the normalization factor of this Slater determinant is 1 divided by n factorial. then we'd write down exactly what we wrote before. So we have the summation over P and Q of the first Okay, so in this case, for what concerns all the coordinates that are not the coordinate of electron I, then for those coordinates, we have just the scalar products. Sorry, I forgot the sign of permutation P and the sign of permutation Q. If the coordinate of the electron is not I, then what we have is just the scalar product between two electronic wave functions. And as it was before, we have to require that if the electron index is different from I, so if for a while we forget the I coordinate and we just focus on all the other coordinates, so if we consider those other coordinates, then we have that P has to be equivalent to Q over so P has to be exactly the same to Q over all the coordinates that are not I. If that happens, we may rewrite this using the following expression. So we have that 1 over factorial n, then we have a summation. Just one step back. If we have the same term, so the evaluation is always the same for all the coordinates that are not I, so P has to be equal to Q. So at the end, we are left with n possible values that come from the permutation of not n coordinates, but n minus 1 coordinates. So due to the fact that here we have exactly the same calculation that we had before, if we forget the coordinate I, for all the coordinates that are not I, that gives us an n minus 1 factorial at the numerator. So we have the same term for all the possible combination of P, because at the end, starting from P and Q, we are just left with P as happened before. And we have to consider all the possible permutations of over all the coordinates that are not I. Then what is left is that we have a summation here over coordinate I over level J So the possible permutations, all the possible permutations over the I index gives us the opportunity to access all the possible levels. So due to that, I replace the effect of the permutation just with summation. So n minus 1 factorial divided by n factorial is just 1 divided by n. So this is 1 divided by n times the summation over j that runs from 1 to n of phi j ri, the operator I, and then phi j times ri. And if you notice here, at this point, I is the coordinate of the electron, but an important thing is that both the structure of this operator and the structure of this operator do not depend over the coordinate. That means if you write down the kinetic operator for coordinate I, you will have the nabla square with respect to the I coordinate. If you switch to the coordinate j, you will have the nabla square for the j coordinate. But the structure of the operator is always the same, so the nabla square of a coordinate. So at the end, the actual dependence over the coordinate I is just a dependence over this coordinate, not on the structure of the operator. So the change of coordinate does not affect the structure of the operator, but just the coordinate of the electron. So it's possible to rewrite this in a more general way, just as 1 divided by n summation over j from 1 to n of phi j r. I leave there the index I just to remember that it was the initial index, and then phi j of coordinate r. So this is just to say that was a one body. No, it's better to remove the index because it may produce a confusion. So A is the general one body operator that acts on coordinate r. And here I just consider the fact that I access all the possible, I apply that operator to all the possible levels. Then this is the result that corresponds just to one of the coordinates, because at the beginning I choose just one coordinate among all the possible coordinates of the electrons. So this is the result that corresponds to just one coordinate. But when I make the summation over all possible coordinates, the summation over all possible coordinates, what gives us as a result? The summation over all possible values of I gives us n times exactly the same contribution, because here at the end we lose memory of the coordinate due to the fact that the actual expression of the operator does not change if we change the index. The only thing that changes is the coordinate. So at the end, when we consider, so if we consider the summation and this is the equivalent of the summation that is performed here. So this up here is the equivalent of this summation down here. This will be n times. Oh, sorry. I just a moment. I cancel here because I forgot to include the expectation value. Just one moment. I rewrite this. So the initial idea was to evaluate this later. I'd write this in a more compact way, just to. So the initial idea is if I have this Hamiltonian, I should in principle evaluate the expectation value over this later determinant of the full Hamiltonian. In this case, I focus my attention on the one body operator. So in principle, I should include here in this expectation value the summation over all possible one body operators. We know that this is equal we have made the calculation for one of those operators, and what we find is that the result is independent of the index. So what we have here is that due to this summation from 1 to n, we expect to have n times the same contribution. So n index, the n value here can be simplified with the n value here. So what we have at the end is that in case we have a one-body operator, the expectation value, if we consider this part of the Hamiltonian that is just a summation of one-body operators, if we consider the expectation value of that over this later determinant, then the expectation value of that is just the sum of all the possible expectation values of the same operator over the electronic levels. So in this picture, this is just the same result we would have obtained in case we consider the single electron picture and not the interacting electron picture. Because if you notice here, you have the expectation value of one body operator over a one electron level. So the summary is, for what concerns all the operators that are found in the Hamiltonian that can be expressed as a summation of single body operators, then the expectation value of those contributions over this later determinant can be just written as the expectation value of the same operator, the one-body operator, over all the possible electronic levels involved in this later determinant. So this is quite easy to evaluate and produces no difference with respect to what we would have obtained, for instance, in the Hartree approach or in a single electron approach without considering the interaction between the electrons. So the final point is, even considering the Slater determinant as the wave function of the n-electron system, so in this way we are able to consider a sort of n-electron wave function that includes the antisymmetry properties that are fine for fermions. So even considering that, the expectation value of the full Hamiltonian over this later determinant can be written as a sum of single level expectation values. So no major changes with respect to the, let's say, Hartree picture, and no major changes from what concerns the independent electron approximation, because also in that case, if you wanted to evaluate the total energy of the system, due, for instance, to the kinetic contribution, you just sum up the expectation values of the operator over all the possible electronic levels, and then you have the final value of the energy. So from this point, from the point of view of, again, of one body contributions, then we have no major changes in the final value of the expectation value. Tomorrow, we will see what happens when we consider the expectation value over a general two-body operator. And here we will have some novelties with respect to the independent electron picture and also with respect to the Hartree picture. And the details of these calculations and the detail of the calculation that I will present you tomorrow are included in a document that I will publish in this classroom this afternoon. So there you will find all the steps of the calculation with some comment on this later determinant and the calculation themselves. Okay. Do you have comments or questions?
No, no questions. Thank you.
Okay. So at this point, I switch off the registration.